The concept of calorimetry. Calorimetry defined as a technique for measuring C. C is specific heat. This is based on the idea of conservation of energy. For example, if we have 100 grams of unknown substance, we want to measure specific heat. Let's mark as Cx because we don't know what kind of material is that. A typical calorimeter system is this. We have a, say for example, aluminum container which is small, and we can fill this container with certain amount of water, and if we know the initial temperature of the system. And then we place this aluminum cup on the rubber ring, and this rubber ring will insulate this small aluminum container from the outside container. So this is the outside container, and between the inner and outer container we have the rubber ring. We have the rubber ring here. So between the outside container and inside container, what we have is air. Air is a very good heat insulator. So we assume what happened inside the little container, it's not going to, the heat is not being able to get out of the system, or outside heat will not be able to get in easily. What we do is, for example, if we have 100 grams of unknown substance, we can heat it up to a certain temperature. For example, we can put into the boiling water, and at normal atmosphere that will be 100 degrees Celsius, and we know that. And we dry this object when we lift it from the boiling water and put it inside. And then we stir the system until they reach a so-called thermal equilibrium, which means it reaches a certain final temperature. By doing so, we will be able to find specific heat for this substance. The idea is this. Now, for example, the energy actually released by the hot substance, it goes to the system which is cold initially. For example, this inner container plus the water. Energy is conserved. That's the main idea behind this. So we say that delta Q absorb, which is by the cold system, plus delta Q of release, which is by the hot system, equals to 0. That is conservation of energy. We assume that what's happened inside will not be affected by the environment. So if we take a look at this, that if absorb defined as positive, and then release must be negative, because only a positive term plus negative term will give us a 0. So let's take a look at how do we use this concept to solve a real problem. Here's example problem 1. If we have an aluminum cup like that of 100 grams, and we have some water inside, 250 grams, and initially aluminum cup and the water are at initial temperature 10 degrees Celsius. Well, usually tap water won't be at 10 degrees Celsius, probably 15, 16 degrees Celsius, but we can lower it by just put a couple of ice cubes inside, and then after it melt, temperature will drop. We want initial temperature to be 10 degrees Celsius. Say we have 50 grams of C, means copper. And we heat it to 80 degrees Celsius. And we have something unknown of 70 grams, and initial temperature somehow is 100 degrees Celsius. We mix copper, unknown solid, with water and aluminum, and place everything inside this, the calorimeter system. We find the final temperature come out at 20 degrees Celsius. So from there, we want to find specific heat, C, for this unknown substance. How do we do the calculation? We learned that the definition for specific heat equals to delta Q over mass and change of temperature. Therefore, delta Q equals to mass times specific heat times delta T. And I would like to point out this equation is only good for solid and liquids. It's not good for gas. And we're going to talk about how do we deal with delta Q for gases. So in this case, we have four substances. So we say M alumina, C of alumina, delta T of alumina, plus M of H2O, C of H2O, delta T of H2O. Well, these two initially are at 10 degrees Celsius and later become 20 degrees Celsius at final temperature. So these two terms actually are delta Q absorb 1, delta Q absorb 2. We expect both turn on positive. And we have this copper. So mass of copper, C of copper, delta T of copper, and that unknown substance, mass of unknown, C of unknown, delta T of unknown, equal to 0. That is conservation of energy. This term is delta Q release 1, this is delta Q release 2, and we expect both turn on negative. So, as a matter of fact, let's look at the number. Now, the alumina is 100 grams. We use, remember we use gram, the unit we use gram as mass, and calorie as the heat. Temperature we use Celsius. Okay, we use this system. So the mass of the alumina times C of alumina is 0.22 in that system. Change of temperature, be careful, final is 20, so 20 minus 10. Okay, let's temporarily just ignore this significant figure. We don't do 20.0. Plus mass of water, and water we have 250 grams. C of water is 1.0, very large. And change of temperature is also 20 minus 10. Both turn on positive as we can see because 20 minus 10 adds positive. Mass of copper, that is 50 grams, and C of copper is 0.092, very small. Change of temperature of copper, copper initially is 80, final is 20. 20 minus 80, that's the change. This turns negative, you see that? And another term is the unknown. Unknown has a mass of 70 grams, and C is unknown. Change temperature, final is 20, initial is 100. So as you can see that if we add four terms together, it is logically it's right because two terms positive, two terms negative, and we can figure out what is the specific heat for that unknown substance. And if we do the calculation, it will come out as 0.48 of what? Because we are in this system that is calorie per gram per degree Celsius. That is the specific heat for this unknown substance. So basically, if we deal with a solid and liquid, and we can use this equation, delta Q equal to MC delta T. However, if C, which specific heat, is a function of temperature, then we have to be very careful. What we need to do is we say that Q equals to of M, since C is a function of temperature, so we should say CT dt, and from T initial to T final. If we know the function of that specific heat with respect to that the temperature, if we know this function, and if mass say is constant, and we'll be able to find by this amount of mass, because of this specific heat function, change temperature from initial to final, how much heat the system needs to absorb. So sometimes we have to do the integral to find Q. 20.3 is a latent heat. Latent means hidden heat. And this is deal with something about phase change. Phase change, well, we have three different phases. For example, solid, liquid, and gas. So it is the phase change between solid and liquid. And when ice melt, okay, and the solid change to liquid. And the liquid to gas, that is water vaporize. So latent heat, it deals with latent heat of fusion, means between solids and liquids. Latent heat of vaporization is between liquid and gases. Table 20.2 of your textbook give us the value of latent heat of fusion and vaporization. The very useful one, L, means latent heat. Latent heat for fusion for H2O, for example, fusion means ice melt. It is 79 of calorie per gram. Every gram of 0 degrees ice, be careful about that. Because if in order to let ice melt, ice has to reach melting point. And the normal pressure, melting point is 0 degrees Celsius. So, and the normal pressure, which is 1 atm, 0 degrees ice, when it starts to melt, 1 gram of that needs 79 calories heat. That's called latent heat of fusion, H2O. Latent heat of vaporization for H2O, again, under normal pressure, which is 1 atm, if we want to vaporize 1 gram of 100 degrees, that's boiling temperature, 100 degrees water, it needs 539 of calories heat. Every 1 gram of 100 degrees boiling water, if we want to vaporize it, I need 539. So table 20.2 give us, first of all, the melting point for a lot of substance. Then give us a latent heat of fusion. And the next column gives us a boiling point of substance, and then gives latent heat of vaporization. And it's quite useful. Now, let's take a look at one sample problem. Mix same amount of 0 degrees ice with 100 degrees water vapor. Water vapor means steam, actually. What's going to happen? Now, we have to be very careful. First of all, ice is already at 0 degrees, so it's ready to be melted. And steam is at 100 degrees, so it's ready to condense. So therefore, because this latent heat vaporization is 539, is far more bigger than this latent heat of fusion. So let's assume this. Let's choose 0 degree as reference. Say m grams of ice, which is 0 degree Celsius, and let it melt, become, well, mass will still be the same. We're still marking it as that, but it's 0 degrees water. We let it melt. So right now, this is ice, goes to water. Then how much heat it needed? So that is mass times latent heat of fusion, because every 1 gram needs this much. Let our steam condense. So m gram of steam, which is 100 degrees, it's at the temperature which will be ready to condense. So it's steam, and it changed to, mass is still same, temperature will still be 100 degrees Celsius, but now it's water, it's condensed. So that is m, because the same amount, see, same amount. So the mass of ice, mass of steam, we use m here, we use m there. But every 1 gram, it's going to release 539, because when we vaporize it, it needs 539 from boiling water to steam. But when the steam condenses, it will give up that same amount, 539. So it seems like that this will release a lot, and the melting need much less. So what's going to happen is, actually, every 1 gram will be able to provide this much. Not only it can melt ice, it also can bring 0 degrees water, right now 0 degrees water, to higher temperature. So say, for example, if we want to bring 0 degrees water to 100 degrees water, let's say continue, to 100 degree Celsius water, how much heat do we need? As a matter of fact, for that part, because delta Q equals to mc delta T, we have this much of 0 degrees water now, it's water, specific heat is 1, change temperature, final is 100 degree, initial 0, those time 100, so it needs 100 M. So for the ice, melting plus increased temperature from 0 degrees water to 100 degrees water, the total actually is 79 M plus 100 M. So it need only 179 M. But as a matter of fact, that steam can provide that much. So what happened is eventually the system will be all the ice melt, all the 0 degrees water goes to 100 degrees, and eventually this is a 100 degrees water and steam mixture. Now, what's the percentage of steam left? We say X gram of steam condense, and each one provide 539 calorie. That will melt and also bring the 0 degrees water to 100 degrees. So have all the ice, okay? Each one, by doing so, you need 179, 79 for melting, 100 for increased temperature. So the ratio X over M, which means how many percent of steam eventually condensed, that is 179 over 539. Let's come back to look at this picture. This part is mechanical equivalent heat we talked about already. This one is very interesting. It's about phase change. Now let's take a look. If we have ice below 0 degree Celsius, which is negative 30, initially we need to warm up to 0 degrees. But once ice reaches 0 degrees, temperature will remain same while it melts. Ice become water. Then, if all ice melt, we continue to provide heat, and the water will start to increase its temperature until you reach 100 degrees Celsius. This is all talk about open to the atmosphere and the normal pressure. Then, when water boils at 100 degrees Celsius, it starts to vaporize. During the vaporization, you see the temperature keeps it constant. All the boiling water changes to steam. So this one is about phase change from liquid to gas. Temperature remain the same at the boiling point. This is melting, remain at the melting point. The idea behind it is that temperature increase means kinetic energy increase. So during the liquid phase, that if we provide heat, the heat goes to kinetic energy. That's why the temperature increase. During the phase change, if temperature doesn't change, it means kinetic energy doesn't change. Now where does the heat go? The heat actually goes to increase the potential energy. Because think about this, from liquid to gas, the volume increases a lot. So the distance between gas molecule and liquid molecule increase a lot, so potential energy increase a lot. So during the phase change, that the heat actually goes to increase the potential energy